This is Unit 10, Part 2 notes over percent composition and chemical formulas. By the end of this unit, you should be able to calculate the percent composition of a compound. You should be able to calculate the empirical formula of a compound, and you should also be able to compare the molecular formula of a compound with its empirical formula. The percent composition describes the relative amounts of the elements in a compound. It is represented by the percent by mass of each element within a compound. And we are going to assume 1 mole of each compound. So we need to use the molar mass as the total mass of the compound. And it's based on the formula where percent composition is the mass of the part divided by the mass of the whole times 100. So just like a pizza, if we have half pepperoni and half cheese, what is the percent pepperoni? Well, you have the mass of the part, which is 4 slices, over the whole is 8. If you multiply 4 divided by 8, which is 0.5 times 100, you would have a 50% pepperoni pizza. Hence your half and half. So therefore, the steps, whenever you are using chemical formulas, first you need to identify the chemical formula. If you need to convert the name to the actual symbols, you need to do that first. Then you calculate the total molar mass of the compound. So separate out all the elements, add everything up, and then you're going to divide the total mass of each specific element by the total mass of the compound. You multiply that by 100 to convert it to a percentage. Therefore, you can calculate the percent composition of the elements within a compound. Calculate the percent composition of each element within propane. So this is an example of calculating percent composition. Propane is C3H8, that's also known as tricarbon octahydride. So we need to make sure we have the chemical formula, which we already do. So the first step, we need to calculate the total mass, or the molar mass of the compound. So we list out our elements. I have 3 carbons and 8 hydrogens. The mass of each carbon is 12, so we have 36. The mass of each hydrogen is 1, so then we have 8. Once we total that together, we have the molar mass of the compound, which is 44 grams per 1 mole. Okay. Then to calculate the percent composition of each element, we take the mass of each element, so the total mass of the carbon is 36, divided by the mass of the whole compound, which is 44. Whenever we multiply that by 100 to get a percentage, it turns into 81.8%. For the hydrogen, we have the total mass of 8 for the 8 hydrogens over the total mass of the compound, which is 44. Multiply that decimal times 100 to convert it to a percentage, and then we get 18.2%. So these percentages represent how much carbon and how much hydrogen is within this compound. To check yourself, if you total up these two values, you should get roughly 100%, if not very close to that. So there's 2 different formulas that we can use to describe the chemical formula. The first one is known as an empirical formula. This is the formula of a compound that is the lowest whole number ratio, that should be ratio, lowest whole number ratio of atoms or moles of elements in a compound. So looking at CH2O, the subscripts are 1 for the carbon, 2 for the hydrogen, and 1 for the oxygen. These numbers are in the lowest whole number ratio. So your carbon, hydrogen to oxygen is a 1 to 2 to 1 ratio. If you can't reduce it any more than it already is, that is an empirical formula. A molecular formula, that's a formula of a compound in its naturally existing form. For example, we have this C6H12O6. That is the molecular formula of glucose or sugar. So we have a 6 to 12 to 6 ratio. However, we can reduce all of the numbers by the number 6 to get that 1 to 2 to 1 ratio. So C6H12O6 is a molecular formula, but it is not an empirical formula. If I were to convert glucose to its empirical formula, then it would look like the first example where we had that 1 to 2 to 1 ratio. So the molecular formula does not have to be completely reduced. It just describes its naturally existing form. Sometimes they can be the same as an empirical formula. For example, ammonium is NH3, where it's a 1:3 ratio of nitrogens to hydrogens. I can't reduce it any more than it already is, plus NH3 is the naturally existing ammonia, so hence the molecular and empirical can be the same. So to calculate the empirical formula from a molecular formula, all you have to do is reduce those subscripts to the lowest whole number ratio. For example, identify the empirical formula of the following compounds. I have C6H12. Those should be subscripts. If I can reduce both of these numbers by the same number, which is 6, your empirical formula of this compound would be CH2, where you would have a 1:2 ratio of carbon to hydrogens. The next example, that is H2SO4. So your subscripts are a 1:2 to 1, to a 4 ratio. Oh, I messed that one up. Erase that. So we have our H2SO4. Sorry guys, I'm remembering glucose right now. H2SO4. So our hydrogen subscript is a 2, your sulfur subscript is an understood 1, and then your oxygen is it's a number 4. So we have a 2:1 to 4 ratio. But can I reduce these numbers, all three of these numbers, by the same number to still get a whole number ratio? No. If there's a 1 here, you cannot reduce it down. So your empirical formula of H2SO4 is still going to be H2SO4. So not only is that a molecular formula, it is an empirical formula. To calculate the empirical formula based on grams or percentages within a question and not based on a molecular formula, we have to follow these steps. You should write down this chart in your ISN as steps to be able to calculate the empirical formula. We have to make sure our mass percent of elements, if we are given a percentages, we have to assume 100 grams. All of the grams should add up, or the percentages should add up to 100 if we are given percentages. If we already have the grams of each element, we will then use the atomic weights to convert to moles. So we'll go from grams to moles, and then from there we'll divide to find the lowest mole to mole ratio of all of the elements. So we can either start with percentage and get down to the moles, or we can start with grams. And in this problem, we have a sample of 13.5 grams calcium, 10.8 grams oxygen, and 0.65 grams hydrogen. And they're asking you to calculate the empirical formula. Well, I'm given grams, so I'm starting at this step right here, where I'm going to use the atomic weights or the atomic mass to figure out the moles. So you write down your givens. If there's 3 elements, we have 3 different givens here. Once you write down your givens, you're going to use the atomic mass to convert grams to moles. This is a 1-step bracket. So there are 40.1 grams and 1 mole of calcium. Grams cancels out. We're left with moles, which they calculated as 0.337. Converting grams of oxygen to moles, again, we divide by the atomic mass. So your grams comes down, moles goes on top. So 10.8 divided by 16, we get 0.675. Then we take grams of hydrogen, and we are going to bring grams down, convert to moles, and then 0.675 divided by 1.01. They got 0.668. Here it's very important to not round too early. So whenever we're doing these calculations, please don't round to whole numbers for the masses of your elements or the atomic mass. So once we convert grams to moles, we now have mole numbers. You have to look at the lowest mole value that you just calculated, which is 0.337. Now we're going to identify the ratio. So then we divide by the lowest mole number there. That's why for every single answer we have, we're going to divide by the 0.337. So 0.337 divided by itself, we get a 1 ratio. 0.675 divided by 0.337, we get roughly a 2 mole ratio. And then the 0.668 divided by 0.337, we get roughly 1.98, which we can then round to 2. So we have the ratio of a 1:2 ratio of the elements, and they're going to correspond with the element that you started with. So calcium is going to have a subscript 1, oxygen will have a subscript of 2, and then your hydrogen will also have a subscript of 2. So we get CaO2H2, This is a rare case where we can put the OH together to make it more of a natural compound, which is calcium hydroxide. The only exceptions here, if you have something ending in 0.5, we can't ever have a 0.5 as a subscript. So if anything ends in 0.5, we have to multiply everything by a factor of 2 to get rid of that decimal. If it ends in 0.33 or 0.66, we'll multiply it by 3, everything by 3 to get rid of the decimal. Or if you have a 0.25 or 0.75, we'll multiply all those values by 4 to get rid of the decimal. To calculate the molecular formula, when given the empirical formula, we need to follow this equation where we have the molecular mass divided by the empirical mass. So all you have to do is just remember M over E. So then for this example, when it asks you to calculate the molecular formula, and you're given a molar mass of 60 grams per mole, that is going to be your molecular mass, which is going to go on the top part of that equation. So then you have the CH4N, so this is your formula, CH4N. So we have the molecular mass here, so we need to calculate the empirical mass. That is your molar mass. So we have 1 carbon plus 4 hydrogens plus the mass of 1 nitrogen. You should total a mass of 30 grams per mole. So remembering this is the effective formula mass or the empirical formula mass. So the molar mass of the molecular over the empirical mass, 60 over 30 gives you a factor of 2. So then we take this 2 and we multiply all of these subscripts by that factor of 2. So 1 carbon turns into 2, 4 hydrogens turn into 8, and then 1 nitrogen turns into 2. So again, you take this 2 and multiply all of the subscripts, and then C2H8N2 becomes the molecular formula. Okay, so I want you to press pause right here and practice these three problems and see if you understand how to calculate percent composition, the empirical formula for number 2, and then the molecular formula for number 3. Number 1 is asking you to calculate the percent composition of ammonia, which is NH3. So we have to first identify the total mass, which is your molar mass. So for NH3, I have 1 nitrogen, which is 14. I have 3 hydrogens, each with a mass of 1, so I get a total of 17 grams per mole. So then to calculate the percent nitrogen, I take the mass of nitrogen, 14, divide it by the total, which should be 17. I'm sorry, it should be 100. So 14 divided by the mass of the compound, which is 17, times 100%. Putting that into the calculator, you should get 82.4% nitrogen. To calculate the percent hydrogen, it is the mass of 3, because that's your hydrogen, over the total mass of 17, multiply that by 100%, and then you should get about 17.6% hydrogen. Adding these two percentages up, it roughly equals 100%, so I know I did the math in the calculator correctly. For number 2, a compound is analyzed to contain 25.9% nitrogen and 74.1% oxygen. What is the empirical formula? Well, we have to first convert percentage to grams, so we're going to assume 100 grams. These two numbers add up to 100, so I can efficiently do that. So I have, for nitrogen, I have 25.9 grams, and then for oxygen, we have 74.1 grams. So I did that first step. Now I need to convert grams to moles. So I make my bracket, and I'm going to convert grams of nitrogen to moles. So 1 mole of nitrogen, there's roughly 14 grams. Dividing that into the calculator, I get 1.85. Doing the same thing for my oxygen, there are 16 grams in 1 mole. This is a gram to mole conversion. 74.1 divided by 16, I get about 4.63. And try not to round too much here. So then I look at the lowest mole number, which is 1.85, so I need to divide both by 1.85. 1.85 divided by itself is just a 1, so my ratio for nitrogen is 1. 4.63 divided by 1.85 in the calculator, you'll get 2.5. Remember, I can't have any subscripts ending in a 0.5, so I'm going to multiply by a factor of 2 to get rid of the decimal. So I have a ratio of 2 to 5, so my empirical formula is going to be N2O5. Using the information from problem 2, if the molecular compound has a total mass of 216 grams per mole, what is the molecular formula? Well, all I have to do is remember M divided by E. This is the molecular mass divided by the empirical mass. My molecular mass is 216, so I need to calculate the empirical mass, which is the same thing as the total molar mass of N2O5. So for nitrogen, there's 2, each with a mass of 14, so that's 28. And then my oxygens, I have 5, each with a mass of 16. That's going to total up to about 80. So 28 plus 80, I should get 108. So that's my empirical molar mass. So 216 divided by 108 is a factor of 2. So I take this 2 and I multiply it through the subscripts of my empirical formula to get the molecular formula. So 2 times 2, you end up, I'm going to change the color here. You get N4, and then 2 times 5 is 10. So you should get N4O10 as the molecular formula. All right, so did you accomplish the objectives of this unit? We're going to first start with percent composition, and then we'll finish with empirical molecular formula on a different day. Just make sure you have these notes written into your ISN, so whenever you get to class, you know what questions to ask me or where to stop me if something in this video confused you.